5, but the general idea of what we're going to do today is most of today is going to be simplifying some trig expressions using a couple different variations of shortcuts, and we'll show you kind of the basic ones that happen a fair amount. And then also we're going to mess with factoring a little bit, factoring trig functions and how that works. That shouldn't be too bad. The factoring should be okay because they're going to tell you to factor, so at least they give you directions on that one. Okay, what's up?
Is the end of the year final just over this semester?
Just this semester, correct. So, so let's go ahead and first start out with, by just kind of going over real quick the main identities that you want to know. The first ones are the reciprocal identities, and that's looks like this. If I have the sine of x, you just want to think about what the reciprocal is for that guy. And reciprocal means you can flip it over in a fraction is the idea. So if you have a number like 5, 1/5 is its reciprocal. Okay, so reciprocal is some junior high teachers will say, right? So the sine of x, what I do is I think about which graph the sine goes with. If I were to graph a sine function, I'd be happy, and then I figure which of the other trig functions, and sine goes with the cosecant, which doesn't really make sense. I don't know why they did that. So 1 over cosecant and sine are going to be equal to each other. So that would be my first thing. And I remember that because these two guys right here, if I were to graph cosecant, I first think of what the sine looks like, and then I flip it over from there. Okay? So that's the general idea with the sine and then 1 over cosecant. Okay? Now, if sine and cosecant go with each other, that also means if I have the cosecant of x, that's going to equal 1 over the sine of x. Okay? So virtually the same thing, you just flip them over. Okay? So anytime you have a cosecant on the bottom and you want to bring it to the top, you can just make it a sine function on the top. If you have a sine on the bottom and you want to bring the sine up to the top, you make it a cosecant. Okay? You can only do that if you're multiplying those. So if I have other things on the bottom that I'm adding or subtracting, then you have to watch out. You have to be a little more careful on that one. But if you're multiplying, you can just do those tricks. Okay? Now cosine of x, you think about the cosine and the other function that goes with it when I'm graphing, or the reciprocal of it, and that would be the secant. So this would be 1 over the secant of x. And then we could obviously do the same on the other side, do the secant of x, and that's going to equal 1 over the cosine of x. Okay, and once again, I match those up just based on which one goes with what as far as the graphs go. Okay, so I look at it more in terms of a graphing thing than it. Okay, so there's sine, cosine, and then tangent of x. Tangent is kind of the easy one. Tangent goes with cotangent, so this is going to be a 1 over cotangent. Those are reciprocals of each other. And then likewise, if we go the other way, cotangent of x would equal 1 over tangent of x. Okay, this is in what they call the reciprocal functions, or the reciprocal family for these. Basically, you're just moving things from a fraction up and down, so on and so forth. Okay. As far as the tangent and cotangent, they have their own. They call them the quotient identities, I think is what our book calls it. Quotient just means fraction. So if I want to write tangent as a fraction, tangent is sine over cosine. So this guy is going to be sine of x over cosine of x. Okay, what's up?
I was just going to ask, what makes it that sine of x is tangent and not cosine of yourself? It's just...
No, that's okay. Where this stuff comes from is if you were to build a triangle on this stuff, if I were to build a right triangle like so, and put it on some kind of xy point, and let's say that's an xy point, this would be your x, this would be your y, and actually your radius ends up being 1. Right? If we're on a unit circle, just to explain where some of this stuff comes from. Okay. Now, if I do the tangent is going to be opposite over adjacent. Opposite is y, adjacent is x. So tangent is really y over x. Okay. Now the y value, if you went from this angle and did the sine function, the sine would equal y over 1, which means that the sine would just equal y. So that's why the sine ends up being on the top there. Okay? If you did cosine, cosine is adjacent over 1. Adjacent is x over 1, so it's just x. So cosine is x, so that's why the x is on the bottom. That's why it's sine over cosine for the tangent. Okay? All right, so a little background there, but you don't need to know too much of that stuff. But the tangent is going to be sine over cosine. Notice this is not a cofunction, so I don't have the cofunction on the numerator. It's just the sine on the top. Okay? If I were to reciprocate that, it's cotangent of x, which is 1 over tangent, which would be 1 over sine over cosine. And if you divide by fractions, you just reciprocate. So it's going to be cosine of x over sine of x. Okay, so if we have a cotangent, the cofunction would go on the top first. That's the way that I remember that. Okay, so cosine over sine for this one. Okay, all right, so there's 3 main categories. There's one of them, the reciprocals, the top section here. This next one's called the quotient identities. And then the last big one that we want to do are the Pythagorean identities. And this actually comes from that same triangle that I just erased. But if I were to do a triangle, sorry guys, I erased it, x, y, and 1. If I did Pythagorean theorem there, it'd be x squared plus y squared equals 1 squared. X is going to be cosine, y is sine. So this really is just going to be sine squared of x plus cosine squared of x equals 1. Say it again. These are called Pythagorean identities. So good old Pythagorean theorem. They come from doing Pythagorean theorem on this triangle right there. So that's why they call them the Pythagorean identities. Okay? Now, that's the first one. The first one usually everybody remembers. Sine squared plus cosine squared equals 1. That one's not too bad. The ones that get a little tougher to remember which ones go where, the ones with the tangents and the cotangents and the secants and the cosecants, there's one that connects those somehow, and it's always tough for some people to remember. So this is where those actually come from. They actually come from manipulating the original one, sine squared of x plus cosine squared of x equals 1. So if you forget, like, what goes with what, you can always match them up later by maybe attempting this, okay? Now, to get the other trig functions, what they do is they actually divide everything here by a sine squared. Okay, and if I divide this by a sine squared of x, this by a sine squared of x, and this by a sine squared of x, that'll simplify to something else for me. The sine squareds cancel, so I get 1 plus cosine over sine is cotangent. Notice they're both squared. If they're both squared, that's going to be cotangent squared. So I'm going to say this is 1 plus cotangent squared of x. And then equals, if I want to bring the sine up to the top, sine is the reciprocal of cosecant. So this is going to be the cosecant squared of x. Okay, so another Pythagorean identity is 1 plus cotangent squared equals cosecant squared. Now, the nice part about this one is, notice the cofunctions actually go together with each other. That's kind of nice, right? Got the cofunction here, the cofunction here. Now, the tangent version of it gets the 1 tacked onto it, and then the cosecant, or whatever the function on the right, doesn't have the 1. A little different than the sine squared plus cosine squared equals 1. The 1's by itself on that one. Here, the 1 is with one of the others. Okay? All right, the last one, you would do this exact same idea, except for instead of dividing by sine squared, you divide by cosine squared. So if I divide by cosine squared on all three of those, I would have sine over cosine, which is tangent. So that would be tangent squared of x. Cosine over cosine would be plus 1. And then it would be 1 over cosine, which is actually secant. So this would be the secant squared of x. Okay, so that's where the third one comes. A lot of times people will write this as just 1 plus tangent, just so it's in the same form. So I'm going to flip that around real quick. It's actually just going to be 1 plus tangent squared of x. Okay? So these are the other two Pythagorean. So there's 3 Pythagorean identities. Now, as far as manipulation goes, we're going to do a lot of simplifying, a lot of manipulation. There's a couple like key things to look for, a couple tricks to be identifying. The first big thing is if I have these main 6 right here, these big 6 right here for the reciprocals, notice that I actually used these in the last simplification, and I used them as they were squared. So if this guy is a sine squared, this guy would be a cosecant squared. Okay? If the cosine was cosecant cubed, this would be a secant cubed. Okay, the powers can work for the reciprocals. Basically, I'm squaring both sides. I'm taking the I'm cubing both sides. I can do anything to both sides on that, and I'm okay. Okay? So there's nothing wrong with changing the powers on the reciprocals. On the tangent, cotangent, same thing. Nothing wrong with changing the powers on there. If this was tangent to the 4th, this would be sine of the 4th over cosine of the 4th. Okay? There's no adding or subtracting for me to mess around. Now, the ones that you really got to watch out for are this sine squared plus cosine squared equals 1. A lot of people want to do sine of x plus cosine of x and say that equals 1. And we can't do that, right? What's the problem with doing this? Anybody know? Kind of weird. There's one thing that screws this up for us. Stinking plus sign, right? Yeah, and the other way is Pythagorean theorem. Pythagorean theorem is a squared plus b squared equals c squared. That's like saying that equals a plus b equals c. That's not necessarily true. Okay, we don't know that. So that's one issue to watch out for. Also, we can't have those be to the 4th power. Okay, if it was x to the 4th plus y to the 4th. That's not Pythagorean theorem. It strictly has to be squares. Okay? So if you have powers and squares, Pythagorean identities are the good places to go. Okay? All right. So one thing to watch out for there. Another thing to watch out for is on the sine squared plus cosine squared, we can actually manipulate this a little bit. We can do the same thing to both sides. And on this one, what I would do, let's say we subtracted sine squared from both sides. So if we subtracted sine squared on both sides, we would get cosine squared equals 1 minus sine squared. So that's another one. Cosine squared of x equals 1 minus sine squared. Now, this actually happens more often than not, believe it or not. But this is not going to be like on a cheat sheet. It's not going to be in your book. They're just going to want you to manipulate that. They're going to want you to see that that's actually good. And I got it from this guy just moving it around. Okay? I could also say that sine squared of x equals 1 minus cosine squared of x. Okay? Those are still kind of in that Pythagorean triple identity. You definitely can use those. They'll pop up a lot, but you're just basically moving stuff around.
And then can you do what you did just above it by cosine or something? I mean, would we ever need to do that?
No. All right, now, with that little trick right here, and I would use this trick a lot. Also, you can do it on this one right here. So if you wanted to manipulate these guys, you could. You could say, for example, 1 can equal cosecant squared of x minus cotangent squared of x. Now, you might not recognize this one right away or see it right away. Things to look for is we have a couple things that are squared and a 1. That's kind of a good hint for us, okay? It's not necessarily the exact same, but hopefully you'll be able to see some of that as we do it. Okay? All right, so let's take a look at some problems and try to work some simplifications, see how some factoring works. But those are the main ones that we're going to use today. Okay? So let's look at that. Let's go super easy. Okay, let's say simplify that. Part of the hard part with simplifying these guys is sometimes you don't know where to stop. It's like, well, how do I know when I'm there, when I'm fully simplified? General rule of thumb is if you can get it down to one trig function, that's great. If you can get it into one trig function, you're probably going to be home free. Doesn't always have to get to one trig function, but chances are a lot of times it gets there. Now, a first strategy to look at is basically what they give you, what type of problem it is. On this one, they give me stuff that doesn't have a lot of powers in it, right? There's not a lot of different powers. So a good strategy is to change everything into sines and cosines. If we make everything sine and cosine, stuff might cancel out. My goal is to get it down to 2 trig functions for everything. Everything I should be able to write in terms of sine and cosine, and so that might help me see where to go. So on this one, I would first change tangent. Change that to sine of x over cosine of x. And then we're going to multiply that by the cosecant. Change that to sine or cosine, which depends on what it is. Cosecant goes with sine, as far as the connection there, and it's the reciprocal. So it's going to be a 1 over the sine of x. And then from there, it's just an algebra simplification, right? We have sine of x's are going to cancel, and so you're going to end up getting 1 over cosine of x. Which we can take that one step further, right? What is 1 over cosine going to equal? Secant. Cosine goes with secant. This would be the secant of x. That's the fully simplified version. Got it down to one trig function. Okay. Now, later in calculus, if and when you guys get there, you'll be doing some kind of harder operations on stuff like this. Simplifying it first is going to be huge. If you can get it down to a simpler version, and then doing the things that you'll do in calculus will make life a lot easier for you. Okay? So that's kind of our big purpose for doing this right now. All right, so that's the first one. Pretty basic. Let's go ahead and make one a little harder. Let's go ahead and do tangent of x sine of x plus cosine of x. Okay, we'll try to simplify that guy. Notice we still have pretty low powers. This time we have a plus sign. So a couple little tricks or rules of thumb. Changing these to sine and cosine is a good idea if my powers are pretty low. Okay, so this one's one where I would take a look at that. The other thing is trying to get things together, trying to actually add trig functions together. In order to do that, you have to have a lot of similarity to happen there. Okay, so on this one, let's go ahead and change things into sine and cosine. Well, that's nice. I've already got 2 things that are already there. Just change the tangent now. Tangent would be sine of x over cosine of x, multiplied by the sine of x, and then plus the cosine of x. Okay, so now everything's in terms of sine and cosine. Might make it a little easier to see what to do. All right, so we'll go ahead and multiply those together. And if I multiply sine over cosine times sine, that gives me sine squared of x. So sine squared of x over cosine of x plus cosine of x. Now, in order for me to add things together like this, especially fractions, we're going to be dealing with a little bit of fractions here, is you need a common denominator. Okay, so a common denominator is a good direction to go on some of this stuff. So on this one, a common denominator here would be a cosine. This guy doesn't have a denominator, or it's 1. So I would need a cosine on the bottom here. So I'm going to put a cosine on the bottom. And whatever I do to the bottom, I got to do to the top. So the top, I need another cosine on the top. That's just going to make it cosine squared. Everybody okay with that? So cosine on the top and the bottom. Now I've got a common denominator. Now I can put those together under one common denominator of cosine of x. My numerator is just going to be sine squared of x plus cosine squared of x, which should be one of those recognizable ones. It's a Pythagorean identity, so that numerator is going to be 1. Okay, another good rule of thumb of things to look for is if you have two things that are squared, either added or subtracted together, then that's a good thing to look for in the Pythagorean section for now. Okay, so this is going to equal 1 for the numerator over cosine of x, which equals secant of x. All right, so that's the general idea of what we're going to be looking at today. Okay, we have a lot more to do, but that's the beginning. All right, everybody feeling kind of okay about this? I started out with some softball ones. Ready for a little harder one? How hard do we want to go?
It's really hard.
You don't. Should we do that one? Nah, let's do that one. Do a hard one?
No.
Yeah.
Medium.
Yeah.
Medium?
Yeah.
Medium
Yes,
hard.
please.
Hard. Go bigger, go. Let's just do that.
I'm just picking. Oh, we're not done. We got lots more to do. Good. Okay, let's go hard.
Can't do it. Too hard? Nah, we'll be fine. Okay, now one thing I might avoid as I start looking at these is, well, first off, getting things together is good, right? There's not a lot of powers here, so some people might change everything to sine and cosine, which is fine. I would be a little cautious on that, just a little bit, because by doing that, you're going to create fractions inside of fractions, and that can get a little confusing on where stuff goes. So if you have multiple fractions, I'd probably try to condense it together first before you do that. And let's see what happens, okay? So for this one, let's go ahead and just do a common denominator there and see what happens. So to do a common denominator between these two, I basically need both of them on the opposite. So I would need on the right one here, this guy is going to need a tangent of x on the top and the bottom. So I'm going to go tangent of x and tangent of x. This guy right here is going to need a 1 plus secant on the top and the bottom. So I'm going to put right here 1 plus secant of x on the top and the bottom. 1 plus secant of x. So there's my common denominator. Kind of gross, but we'll figure it out. So my denominator for all of this is going to be 1 plus secant of x multiplied by tangent of x. Looks pretty good. The numerator is going to be secant of x times 1 plus secant. So let's go ahead and multiply those together. So secant times 1 is secant of x. So I'll have the secant of x here. Secant times secant is plus secant squared. So secant squared of x. And then minus, we have tangent times tangent, so that's minus tangent squared. Okay? Now, sometimes there's things that are a little hard to see, but notice I have a couple things that are squared in there now. That's pretty good. That might fall into the Pythagorean identities for me. I have a secant squared minus a tangent squared in the numerator right here, right? Equals 1.
It equals 1, right? Because we have, the trick was, I think our identity was 1 plus tangent squared equals secant squared. So if we subtracted a tangent on the other side, this would all equal 1. So this stuff right here, from here to here equals 1. Okay, that right there. Secant squared minus tangent squared. So I'm going to have secant of x plus 1 divided by 1 plus secant of x multiplied by tangent of x. Which cancel out, okay. Now we can cancel because I'm multiplying these two guys right here, right? So cancel is good here. So 1 plus secant, secant plus 1, those guys cancel. And I'm left with 1 over tangent. Which is cotangent. Okay? Tangent and cotangent go together, so you can reciprocate those. Okay? So, a little more complicated, a little more challenging there. Let's take a look at one where we're going to have to factor now. Question, yeah?
So on these ones, did you say not to multiply out the denominator?
I'd probably say not. The only reason is well, first off, I kind of saw that there was stuff on the top as secants, so I figured something might happen there. The other thing is these were different trig functions, so multiplying those together might not help me too much. So, anyways.
How'd you get the 1 on top again?
Oh, from right here to here was 1.
How do we know? How
Because on the Pythagorean theorem, I have 1 plus tangent squared of x equals secant squared of x. Right?
I'm trying to find.
Wait, the answer's cotangent?
The answer's cotangent. Yep.
What if
So, if I wanted to get from here, now, unfortunately, this is not an identity you'll probably recognize right away, but it is a couple squares next to each other. So that's where I would start looking at these, okay? So, from this guy right here, if I want to get this, all I would do is subtract tangent on both sides, giving me 1 equals secant squared of x minus tangent squared of x. Okay? So that's kind of the way I would go about that one. Secant squared plus 1, secant squareds cancel, and we're home free. Okay? Alright, so other ones. Let's take a look at some where we're going to have to do some factoring now, okay?
no, secant.
That was a little bit tougher one, I know.
That one was really.
Can we go
Let's
to medium?
do
Make it cry.
make it cry.
Please don't.
Okay, this one actually won't look simplified. It's just a practice in factoring, okay? And we'll look at some other stuff in a minute.
You're supposed to factor it?
Yeah, let's just factor this. Just want to factor this. Now, we're not really going to simplify this one. We're just going to, some of them you're going to just factor. Sometimes when you factor, good stuff happens. Now, this one, I know that factoring is a good idea because I've got a different level of x's, or a different level of trig functions here on this one. So I've got something squared and something that's not squared, and I would think of this as basically x squared minus 3x minus 10. I would think of it algebraically as that problem right there. So if I were to factor this guy, it's a pretty easy factoring. It's just a matter of seeing it in terms of with the sign function. So if I were to factor this guy, I would factor this to x here and x in here, and then factor negative 10 to add negative 3 would be
5 and 2.
5 and 2. So negative 5 and positive 2. So negative 5 and positive 2. That would be if I were to factor just the basic algebra factoring here. Now I'm factoring with trig functions. The nice thing is it's the exact same. Instead of the x's now, just put signs in there. So this is really just going to be the sine of x minus 5. And it's going to be the sine of x plus 2. So that's the factor version of this guy right here. Okay, so some of them will just have you factors. They'll just be factoring a trig function. Later in the chapter, that's going to be a really good thing. Get it to a factored form once we start solving stuff. Okay? All right. So that's the factoring one. Let's go and do a simplified one where you maybe want to try to factor. And I'll show you what that one might look like. Let's just go medium on this one. Let's not go super high. Let's do that one. That's a good one. How about cosecant squared of x, cotangent of x, minus cotangent of x. Okay, so let's fully simplify this and see what it falls down to. Then we'll just do one or two more and be good. Now my advice would be to try stuff. Even if you don't think it's going to be right, just try stuff. Sometimes when you try stuff on this, it at least tells you, what might be going on, or you only have so many different strategies to try. So change things to sine. Cosine is a good thing. Looking for squares together is a good thing for the Pythagorean. Factoring is going to be a good thing. Since I just showed you factoring, we might be factoring on this one. Just throwing that out there. So if I were to try to factor this one, if you thought about this as an algebra style equation and I said factor it, I would probably make it look like this. This is really x squared multiplied by a different trig function, so that's probably like a y, and you can make it whatever letter you want, minus the same trig function as before, so y. So if I said to factor that guy, what kind of factoring would you use on that? A common factor, take a y out of both of them, right? So I want to do a common factor. Notice there's a cotangent in both, or there's a y in both. You can take the same thing out, it would end up looking like this. Y on the outside, and then it would be x squared minus 1. Okay, and I just took a common factor out. Now instead of y and x, I'm just going to use cotangent and cosecant. So my common factor between these two is cotangent. So I'm going to take a cotangent out, cotangent of x, and then on the inside I'll be left with cosecant squared of x minus 1.
Is that it?
Okay, well we're actually, if for the factoring, yes, that's it. We're going to actually simplify this and keep going on. Okay, factoring might just be the first step on this. Now, a good thing to look for, I think, is we have something that's squared next to a 1. Automatically, you guys should be thinking Pythagorean, right? Look at the Pythagorean section and see if you can get something like this. Now, there's only one with cosecant, and that's the one with cotangent, right? So it's 1 plus cotangent equals cosecant squared. So to get cosecant squared minus 1, what would this all turn into?
Cotangent squared. Perfect. So this all here is cotangent squared of x. Multiplied by cotangent of x. And so we'll just multiply those two guys together. Cotangent cubed of x. And you're done. Okay? So, factoring at the beginning might lead us up to a nice little Pythagorean identity. Might do some other things. And we're happy. What's up?
Will they tell us what they're
What do you mean? Like where you should get to?
like?
No.
Are they going to ask us to factor?
Oh, like factor here first and simplify. Sometimes they will, sometimes they won't. It just depends on the problem set. Like there's a bunch of different little mini problem sets. Sometimes they make you do certain things. Okay. Now another thing that you could do, and this is my brain would probably work this way as well, is I would see this problem, and let me erase this. I hope everybody's okay that I erase that. I would see this problem, and I would think, I always think back to Sesame Street. You guys remember watching Sesame Street when you were a kid? They always had this game where they had like 4 quadrants, and then they had like 3 things that were the same, and then one that was different. They had a cool song. Which one of these is not good? Anyways, they had a cool thing like that. My brain sees this problem kind of like that, right? I've got a couple cotangents, which is great. I got this cosecant that's not a cotangent, right? But maybe I want to switch this. Maybe I want to make that a cotangent if I can. So I would look in the Pythagorean identities and say, all right, well, what can I make cosecant squared equal in terms of cotangent? And I can make it equal 1 minus tangent squared, right? Or no, I'm sorry. What's our identity? It's 1 plus tangent squared of x equals cosecant squared. Oh, I screwed that up. Cotangent. Sorry. 1 plus cotangent squared of x equals cosecant squared. Okay, now as I look at this, cosecant squared equals 1 plus cotangent squared. So I could put a 1 plus cotangent squared right at the beginning. I could say this is 1 plus cotangent squared of x multiplied by cotangent of x minus cotangent of x. Okay, everybody see that? Now they're all the same at least. If they're all the same, stuff might work out a little nicer for me, right? Now, as I distribute the cotangent through, it would give me cotangent of x plus cotangent times cotangent squared is cotangent cubed minus cotangent of x.
That's easy.
Might be easier than factoring, right? So there's other ways around doing these problems. And you guys probably remember from the past, there's more than one way to solve these guys, okay? So just because you don't see the right way to do it right away doesn't mean you can't get there by another method, okay? So same answer, feeling good. Let's do one more that's a little trickier and then call it a day. Once you guys practice some of this stuff. Ooh, how hard do we want to go? Oh, let's do that one.
It's always harder than it looks.
Let's go ahead and simplify this. This one will be a little tough. Write this so it's not a fraction. Gross. Basically, we're going to try to simplify this as best we can, but I don't want a fraction when I'm done. If I can eliminate my fraction, that's always a good thing with eliminating fractions. I like doing it. Okay? Now, notice what I have here. I've got a 1 and a sign right there, right? Now, a 1 and a sign next to each other, that's usually the Pythagorean area, right? Now, the Pythagorean, what's the Pythagorean that has the 1 and the sign with it? Sine squared plus cosine squared equals 1, right?
That would be an 80.
Okay? Now, exactly. Now, if I were to try to get like a 1 and a sign on the same side as each other, I'd have to move this sign on the other side. I'd have to go cosine squared of x equals 1 minus sine squared of x. So I'm close. The other thing to notice is what's different about this guy and this guy? Well, one's squared and one's not, right? So somehow I got to get this guy to be a 1 minus sine squared so it looks like that. Well, what can I maybe multiply this guy by to get 1 minus sine of x? Yeah, if I do 1 minus sine of x, notice that those are conjugates of each other, right? And we've done conjugates before. Same binomial, just with the opposite sign. Now, if I FOIL these together, conjugates outside and inside always cancel. And so you just basically have the first and the last term. 1 and 1, negative sine squared. So that's where you get 1 minus sine squared. Now, I have to do that to the top as well. Okay, so I'm going to multiply the top by 1 minus sine of x. Okay, so to get rid of a fraction, you can conjugate. That conjugation will help you eliminate some of that stuff. So 1 times 1 minus sine is 1 minus sine, divided by 1 minus sine squared. You're like, well, wait, I just made that harder. It doesn't look any more simplified. However, 1 minus sine squared, that's a good one. What is that going to equal? Cosine squared. So this is going to equal 1 minus sine over cosine squared of x. Now, the ultimate goal for this, at least I think,
is to get rid of the fractions. Okay, that's what we really want to try to do, is get rid of the fractions. So on this one, to get rid of this fraction, let's do something called splitting a fraction. Let's go ahead and split this fraction and see what the two parts would be. I have a denominator of cosine squared. I can give each of the numerators that denominator. I can write this as 1 over cosine squared minus sine over cosine squared. Okay, basically working backwards a little bit. Normally I'd try to be combining those. Now I'm separating those two. I'm splitting them up. Now 1 over cosine squared, I can make that not be a fraction, right? That'd just be secant squared, right? So this is going to be secant squared of x. That's pretty good. And then minus, we got sine over cosine squared. Now that doesn't match up very nicely, right? But we have sine over cosine, right? What does sine over cosine normally equal? Tangent, right? The problem is I have an extra cosine on the bottom, right? So what you can do is, instead of that square right there, you can write that as cosine times cosine. Sine over cosine is tangent of x. And then I'm left over with this extra little cosine on the bottom, right? Well, if I want to move the cosine to the top, it becomes secant. So I'd have a secant of x like so. Now I no longer have a fraction. It's kind of cool. Okay, so that's the general idea with getting rid of fractions for these guys. Conjugating the denominator, and then trying to split that fraction up and then simplifying it from it. Okay? Now the problem is, what's that? You can factor if you want. Take a secant out, it'd be secant of x, and then it'd be secant of x minus tangent of x. Like so.
Where'd you get the secant out of there?
Where'd I get the secant out? Okay, this part right here became tangents, right? So I still had a cosine left over on the bottom, right? This fraction's still over there. 1 over cosine becomes the secant. Okay?
I know, and I just.
And I know it's kind of tough to see that split right there, but you'll get probably used to it a little bit. I'm okay with either one of those answers. It doesn't really bother me which way you leave it. It kind of looks like you would say, well, doesn't look fully simplified. And you're right, it's not. But for your calculus purposes, this is going to be way better later on to have it simplified in this fashion than in the original one. With this fraction, this would be really hard to do some of the things you'll end up doing later. Okay? So that's kind of the strategy that we're going to be headed towards for some of this stuff.
How do we know that you're okay with that answer?
How do we know that I'm okay with that answer?
You specifically.
What do you mean?
Like, I don't know.
Because it's not just
How
one.
can it be simplified down more?
How would you, if you wanted to try to force it a little, I don't know if you're going to ever get it more simplified. To me, like my opinion, that looks way more simplified. My opinion, it's got less trig functions. There's a fraction, but it's got less trig functions, right? But the goal on this one was to get rid of the fraction in itself. So that, unfortunately, is a lot prettier than the other, as far as the stuff that you'll do later down the road. When you start integrating it, start taking the derivatives of it, it's easier to do it in this form. I hate to just leave it at that, but I know it doesn't make a lot of sense now, but it'll make a little more sense later on when we get there. So, all right, so we are on 345.